Every good day, the topic I've chosen for this project is predicting soccer match outcomes with confidence scores to support smarter betting decisions. Every day, millions of people place bets on soccer games, but most do so based on gut feeling, biased opinions, or surface-level stats. This often leads to poor outcomes and low trust in betting advice services. There's a clear opportunity to use machine learning to provide smarter betting insights. Here's why it's a great fit. First, the problem requires prediction, not just computation. Soccer match outcomes are uncertain and require probabilistic models, not simple math. Second, there's a wealth of available data, like past match results, team performance, betting odds, and even weather conditions. Third, a predictive model would create real business value. It could boost user trust, increase engagement, and drive subscriptions on a betting tips platform. Now let's walk through the business understanding phase using the CRISP-DM framework. The business objective is to improve user engagement and trust on a soccer betting tips platform by offering machine learning-based match predictions with confidence scores. Our data mining goal is to build a classification model that predicts whether a match will result in a win, loss, or draw, and assign a confidence score to each outcome. We'll measure success in two ways. Outcome metrics, like user engagement with tips and growth in subscriptions. Output metrics, like model accuracy, precision, and how well our confidence scores are. The model will use a range of features including recent team performance, player injuries, historical matchups, betting odds, and match context like home/away status. Here's our machine learning solution concept. We'll develop a classification model that uses match-related inputs, like recent team form, injuries, and betting odds, to predict the probability of a win, draw, or loss for each soccer game. These predictions will include a confidence score to help users identify which matches are more reliable to bet on. To train the model, we'll experiment with both interpretable algorithms like logistic regression and random forest, as well as more powerful methods like XGBoost or neural networks for more complex feature sets.
To validate this solution, we'll take an iterative approach. First, we'll test the model offline using historical match data to evaluate its predictive power. We'll focus on metrics like accuracy and whether our confidence scores are well calibrated. Next, we'll run shadow tests on upcoming matches. The model will make predictions behind the scenes, but they won't be shown to users yet. This helps us verify performance without affecting the user experience. Finally, we'll run an A/B test. For the ML system design, we made 3 key decisions. First, we chose batch prediction instead of real-time. Since matches are scheduled in advance, we can generate predictions once a day, which is more cost-effective and simpler to maintain. Second, we'll retrain the model on a weekly basis. This helps the model adapt to changes in team performance without reacting too strongly to short-term fluctuations. Lastly, we'll use a human-in-the-loop approach to start. A sports analyst or domain expert will review model outputs before they're shared with users. This helps maintain quality and build trust early on. If the model performs well over time, we can gradually transition to a fully automated system. Now let's examine the potential risks our soccer match prediction model might face once deployed in production. Being aware of these issues helps us build monitoring systems and mitigation strategies from the start, ensuring our model remains effective over time. The first major risk is data drift. Soccer teams are dynamic, star players transfer between clubs, coaches implement new strategies, and team chemistry evolves. If key players like Messi or Holland change teams, our input data distribution changes significantly. A model trained on historical data with players in certain teams may perform poorly when those players move elsewhere. We'll need to monitor feature distributions and retrain the model regularly to address this. Concept drift occurs when the fundamental relationships in our data change over time. For example, Home field advantage, historically a strong predictor, significantly decreased during the COVID era when stadiums were empty. Similarly, rule changes, new coaching philosophies, or evolving gameplay tactics can all change how our features relate to match outcomes. We'll need to track prediction accuracy over time and implement automated alerts when performance decreases. While our initial system uses batch prediction for upcoming matches, we may eventually want to offer live in-game predictions. This introduces latency concerns. Can we process streaming data and update predictions fast enough to be useful for live betting? Our batch approach helps mitigate this for now, but we'll need to consider edge computing or optimization techniques if we move toward real-time predictions in the future.
Finally, we face the risk of creating unintended feedback loops. If our prediction system becomes popular, users may place bets based on our recommendations, potentially influencing betting odds. Since betting odds are one of our input features, this creates a circular dependency where our model influences its own inputs. We'll need to carefully monitor for this effect and potentially adjust how we incorporate market-derived features into our model.